4, 6, 8, 10, 12, 13.
Yeah, let me just.
Pretty close, actually, to everybody.
I think you should record it anyway.
What's that?
Oh, you are.
Yeah, I record it every day. And I've been giving them all out every day. So. Yeah, there hasn't been that many people that watch it, though. You get to see how many people, and you get to see, like, haven't done it this semester, but I assume it's the same. How, like, engagement, like, how long do you watch? Most people watch like 3 minutes and then they stop. So I know my voice is so riveting, you probably just fall asleep. Okay, so we started talking about this idea of stress transformations, right? Because even though we might analyze a given element, that analysis that we conduct is developing what the stress state at a given orientation, right? So in this case, we had this axial loaded bar, right? It had an axial load on the bar. We cut it at a perpendicular plane, right, to understand what the normal stress is. But then if we cut it at a angle, right, we essentially develop these normal and shear stresses on that plane, whose components add up to the original axial load, right? So at an orientation, we essentially will get shear and normal stresses acting in an element, okay? And when we start combining loads and not only have axial loads, but say torsional loads, we added axial and torsion loads together on that example a little bit ago, right? And we figured out the stress state. And in those, we had shear stress and normal stress, okay? And so when we're faced with that, in order to develop what is the maximum stresses the element's going to see, both maybe for shear stress or for normal stresses, we use Moore's circle, which I figured out was a German guy, okay? Actually in the 1880s, I came up with that. And it's essentially a visual representation of the stresses at a point in our element, right? Oriented at any angle. So we're gonna go through and we're gonna figure out what the stress is at a specific orientation. In our case, right, we looked at point A, which was where we had a perpendicular plane that was running in our axially loaded element. So we just had a normal stress. We had no shear stress, tau xy and tau yx. We had no normal stress on the y face either. And we just had an axial load acting in one direction. So we plotted those points, which you do for any known stress state. And based on those that known stress state, from that known stress state, we can develop this circle, right? Because we're essentially plotting our 2 points. We've got sigma x and tau xy. That's our normal stress and our shear stress on the x faces. That would be one of our points, our x and y coordinate. Our other x and y coordinate is the stresses happening on the y face, right? So we have normal stress in the y direction and shear stress on the y faces. And we'll plot those. Based on that, those 2 points, we can then develop this circle. And what this circle gives us is all of the stress states in this element, right, at any orientation. And based on our mechanics derivation before, we came up with these 2 equations that relates the stress, right, the normal stress and the shear stress on any plane, right? So if we changed theta, we did this, it was in a homework, you guys figured out what the stresses were on an inclined plane on an axial loaded element. So if you did that, you essentially develop these 2 equations that give us what that stress is. Well, Moore's circle essentially puts those into a larger depiction that allows us to incorporate both torsional stresses, axial stresses, bending stresses all together into one, okay? So as I mentioned, we have a y-axis, which is our shear stress, okay? Our counterclockwise is in the bottom portion of our diagram, right? The positive side, the negative side, which happens to be the top of this diagram, thanks to Moore, okay? Whatever shear stress is in the clockwise direction, that gets plotted up here. We have normal stress, which is positive to the right? So tension is on the positive axis. In the x-axis, negative side is compression. So we plot our points, we make our circle, and it allows us to develop what are our maximum stresses in our element, right? We have maximum shear stresses. Well, that's going to be the top and bottom of our circle, right? Equal and opposite. We know that. Tau xy equals tau yx. So we can figure out what orientation our maximum shear stresses are going to be based on our initial stress configuration. So in our case, we have this stress block A. We landed on our Mohr's circle, right, on the x-axis. And so if we rotate 90 degrees on Mohr's circle, we essentially would develop what our maximum shear stress is in that element, okay? And we could figure out what that stress state would be. So if we drew a block, right, and it was A again, and this A was at 45 degrees. Right, so if we were looking at the stresses on these faces, they would be our maximum shear stresses. And our, also at this point, right, we have a normal stress. Right? It's got an x coordinate also. X coordinate is the same. So we're going to have a normal stress on the x face and a normal stress on the y face as we rotate these 2 points over. So we're going to get, right, in this case, we're going to have a tension stress on both faces that are equal to essentially the average stress, right? The stress is the halfway point between our initial maximum normal stress, and then we had 0 on the y face, right? As mentioned, Mohr's circle, right? Every angle of rotation on Mohr's circle is twice that in the real world, okay? So if we rotate 90 degrees from our initial rotation, right, A, we were oriented at 0 degrees. If we rotate 90 degrees to that, right, we're really rotating 45 degrees. So if you cut a plane, go back up here, and we cut a plane through this at 45 degrees, right? We cut a plane through this axial member at 45 degrees. The shear stress on that plane is going to be the maximum, right? And we'll also have a normal stress on that plane. Okay. If we wanted to look at, say, any angle, right? So say this. We wanted to look at the stress oriented at 60 degrees from our initial stress plane, right, AA. We would merely go up. We would determine that alpha equals 2 times theta. It's 2 times 60 degrees, right? So 120 degrees. We would rotate alpha 120 degrees. We would develop a line. Whoa, shit. Something like that, okay? We would have our 2 points, right? So our sigma x and our tau xy. Now we rotate 120 degrees on this circle. We would then be able to figure out, right, what is our tau b xy is now up there. This would be our sigma bx. This is our sigma by, and this is our tau byx, right? Essentially the coordinates of these 2 points now become the stresses on our stress block if we were to orient, right? So if we took, given that we knew the stress at AA, right? And we wanted to rotate and look at a stress plane that's at 60 degrees. So we orient our block at 60 degrees, we would have a sigma bx. We'd have our taus. We have our sigma by, tau byx. This is tau bxy. Right, and this is oriented at 60 degrees. So we can really figure out what stress is at any orientation on any plane within our element by initially knowing an initial stress state, right? So we can plot it, create the circle, and we move on from there. Any questions? All right, so if we look at this chart again, which I had before, do something like this. All right, so this is sigma y. This would be sigma x, and this is tau xy or tau yx. So that's the shear stress, and that's how it varies as we go through our different planes, right? At 0 degrees, that's our AA plane. We've got all normal stress. We've got 0 shear stress. We've got 0 normal stress in the y direction. As we rotate around the circle, right? Once we get to 45 degrees, we have our normal stress in both directions equal to each other, and we have our maximum shear stress. Again, we continue to rotate. We go 90 degrees, which would be 120, or which would be 180 degrees on Moore's circle, right? So this is effectively 90 on Moore's circle, or 45 in the real world. When we get to here, we're at 180, so that's 90 in the real world. Once we get to 90 in the real world, right, we get to this 0 shear stress, 0 normal stress in the x. We've got all the normal stress in the y. We've essentially taken our stress block, right? Our stress block A, rotated at 90 degrees. Well, what does that do? That just means that now the y face has this normal stress on it, right, that we're pulling on. So that's why as we rotate 180 degrees, okay, we rotate 360 degrees on Moore's circle. All right? Let's do some examples so you guys don't look at me like I'm crazy. All right. So we're going to do it a couple different ways. We're going to do it the way that we derive the equation for this behavior, right? And then we're going to use Moore's circle. So we got a 10 millimeter thick bar, okay, about ½ inch thick bar. And we wanted to, and it's loaded as shown, so we got 180 kilonewtons, okay. We want to determine what's the max normal stress and the normal and shear stress in an element rotated at 57 degrees. First, we're going to use chapter 1, which we used equilibrium, where we just cut it, figured out what the components of those forces needed to be, and we could develop what the shear and the normal stress is on any given plane, right? That's what we did in chapter 1. And then we're also going to use Moore's circle, okay? So the max normal stress, as we know, is going to be oriented at a plane that's perpendicular or normal to the applied load, right? So we're just going to cut it vertically. Maybe you guys can see this better. Okay, we're going to cut it vertically, or a plane that's normal to the applied load for our maximum normal stress. So that is, we're going to call this block 1. It's going to have a normal stress on it. It's going to be very similar to our block A up above, right? Cut a plane normal to it. We're going to have this force over an area, the area being the bar, right? Because we know that sigma max equals P over A. In our case, we have 180 kilonewtons or 180,000 newtons. The area, well, we've given it's 120 millimeters wide and it's 10 millimeters thick. We get 150 newtons per millimeter squared. So we say sigma max is 150 megapascals, right? Or newtons per millimeter squared. Yes, Brandon.
And then where is block 1 oriented? Is that on our cut?
Yes, so block 1 would be like placing a block right there.
Okay.
right? So this would be block 1, okay? Where we're cutting the section and we're looking at the face of our block, our stress block, right? Knowing that the normal stress on that block is force over an area. We know the force, we know the area. Okay? Now, they ask us for the normal and shear stress in an element rotated at 57 degrees. Well, so part 2, we are going to look at this cut here, right? And that cut there, we really want to look at what's going on, right, on the face of this block that's oriented at 57 degrees. Right? We're going to cut, we're going to look at this little block of material, right, that's oriented normal to that cut. And we're going to look at what the stresses are. Right? So this guy's going to have some normal stresses and some shear stresses. Right? Something like that potentially. Okay? We're going to calculate those. But first, we're going to calculate based on what we did in, if we oriented that block normal. I mean, it is rotated, but we're going to normalize it here. Just put it straight up. It's going to look something like this. Right? We've got tau xy and tau yx. We have sigma x, right? Sigma y. So we're going to have this stress block. And it'll potentially have stresses on all 4 sides. We're going to figure that out based on these 2 equations we had before, right? That we derived in chapter 1. That said the normal stress was P over 2 times the area times 1 plus the cosine of 2 theta. And then we had one equation that said that the shear stress, or tau xy or tau yx, is negative P over 2a times the sine of 2 theta. Right, where this angle is theta, right? Orientation of that line with respect to theta. So this all came from chapter 1. So if we go through and we plug and chuck, so for sigma x, right? So that sigma x in our case is this face that's along our cut. We're looking at the x face being the one along the cut. We're going to say sigma x equals P, well, that's 180,000 newtons, 2 times the area. Well, we said we were 120 millimeters times 10 millimeters. 1 plus the cosine of 2 times 57. Okay, well, we get a sigma x equal to 44.5 megapascals. And we get a tau xy equal to negative P over 2a, right? So 180,000 over 2 times 120 times 10 times the sine 2 times 57, a lot of parentheses. We end up with a tau xy equal to negative 68.5 megapascals. If we wanted to know what was going on this y face, right? This y face, we would need to look at a cut plane that is running along that face, right? So we're no longer going to cut it right here. I'm going to cut it at 90 degrees. So if I take this, now I'm going to run a second cut. It's going to do something like this. If I run this second cut, the angle here is going to be 33 degrees. Right? This is 57, this is 57, this is 90. 90 minus 57 is 33. That's gonna be this angle there. So if we run this number, right, if we look at sigma y equals 180,000 newtons, 2 times the area, 120 times 10 millimeters, 1 plus cosine 2 times 33. We end up with sigma y equal to 105.5 megapascals. And we know tau xy has to equal tau yx, okay? But if we put in sine of 2 times 33, you're going to get the exact same answer. We would get 68.5. If we go to calculate tau yx, we did tau yx in order to figure out what is the shear stress along the y face. Right? We're going to look at a plane that's oriented along the y face. It's oriented at 33 degrees. So you plug that into our tau equation, and we're going to get the exact same thing. So validating that tau xy equals tau yx. So we end up with 44.5 megapascals of a normal stress in the x face, shear stress of 68.5, and then a normal stress on the y face of 105.5, okay? Now they ask us to go through via Moore's circle. So if we start our Moore's circle, again, these coordinates are skewed based on knowing how this is going to land. But you could have points that are on the left-hand side, right, if this was in compression. So I'm going to plot 2 points on my Moore's circle, right? So I just have to pick a known stress state. I'm going to pick this stress state 1. I'm going to cut this bar. And I know that it's normal stress, sigma x, equals 150 megapascals, okay? I know there's no shear stress on it, right? We don't have any torsion, or we don't have any bending on it, so we don't have any shear stress. We just have an axial load. So that also means that our stress in the y direction is 0. So that means that we get to plot our 2 points, and we're going to plot them. I'm going to plot them as, again, our sigma x, right? Sigma x, tau xy. In this case, it's 150 megapascals, right? 150 megapascals, comma 0, because there's no shear stress. So that's our coordinate for 1 point. That's our x face coordinate. Our y face coordinate, sigma y, comma tau yx. Well, that is 0, comma 0, right? It's at the origin. We have no normal stress. We have no shear stress. So we get these 2 points. So this is when I'm going to have to get good at this.
That's cheating.
That ain't bad. I'm going to draw a circle. Yeah, fuck you guys. That's awesome. All right, so we got our 2 points. We scribe a circle, right, between those 2 points. The average of which of our normal stresses, that's our center. So that would be right here. That's C. Well, in this case, it's 75 megapascals. But if we wanted to figure out the actual equation for this, it's pretty easy in this case. But sometimes we've got these weird... Whoops, what am I doing? I'm jumping ahead here. Got me all excited. So the center is our average stress. Well, that's sigma x plus sigma y over 2, right? That'll always be the case. The coordinate, the x coordinate for our center, right? It's always going to be y coordinate is 0 because our shear stress, no matter where we plotted points on this stress block, our shear stress is equal on both faces. So we're going to be on equal sides of our x-axis. And so we're gonna have a center that sits on the x-axis, so our tau is 0, and the stress value is the average stress. So it's essentially sigma x plus sigma y divided by 2. In this case, right, we have 150 plus 0 divided by 2, 75 megapascals. So that's our coordinate, right? 75 comma 0. 75 comma 0. Well, if we are interested in looking at a point oriented at a given angle, right, we're going to really want to know what the radius is. Because as we travel around this circle, that radius is going to help us determine what is our normal stress and our shear stress as we make our trip around. And so as we do that, right, we're going to say be up here and down here. That angle we've established is alpha. These points, right, this will be sigma x comma tau xy. And this is sigma y comma tau yx. I guess I should probably add in that this is shear stress, right? Positive. We have counterclockwise rotation below the x-axis, clockwise above. This is also sigma normal stress, right? Positive to the right, or tension. So as I mentioned, we're going to really want to know what the radius is, because once we know what the orientation is, we know where we're going to land on the circle, and we can develop what our normal stress and our shear stress is. So I'm going to tell you that the radius is always sigma x minus the center squared plus tau xy squared square root. Which equals sigma x plus sigma y over 2 squared plus tau xy squared. Right? Essentially the average stress squared plus the shear stress squared square root, right?
You got rid of a sigma x.
I got rid of sigma x and the center and replaced it with the average stress. Because sigma x minus the center is the same as saying the average stress. This magnitude here, the center, is always going to be this, like the magnitude between these 2 points, right?
Yeah.
Which is the average stress.
I thought just C was equal to the average stress.
C is the center, which is our average stress. How did that work?
It's our radius.
Yeah, but it's sigma x. Now you see I had it, and then you made me lose it. Sigma x plus sigma y divided by 2 squared. No, I think you're right. I think what I ended up doing is,
Yeah, because your center is not always going to be equal to
Nope.
the radius if your minimum.
agreed.
stress
If
is
you're
not
if you're
equal.
like if the circle was either way to the left or way to the right, it's not always going to be equal. But this one, that upper one makes more sense, right? Because you're always this minus the center is always going to give you this distance, right? And it's that distance that you can establish what the radius is. No, you're right. All right, shut this down. Get rid of this, huh? I'm going to double check, and we're going to have words eventually. I think it is right, but I need to wrap my head around it. It's not worth wasting our time right now, okay? So, sigma x minus the center squared, right? Essentially figuring out what's our x coordinate and what's our y coordinate. Pythagorean theorem, right? Square root of the sum of the squares. That'll give us our radius. So in our case, we know sigma x We know the center, and we know tau xy is 0, right? For our known stress state. So that means our radius is 75 megapascals, which you can see if you draw a nice circle like I did, you can see that. Okay? Maybe if it's scribbled up here, it's kind of hard, but obviously this radius is going to be 75. So if we look back and we're trying to answer our question 2, right? Where we had a theta equal to 57 degrees. Well, if theta is 57, we're going to move alpha in Moore's circle, which is 2 times theta. Well, that's 114 degrees, right? So if we look at a stress cube, and I'm just guessing on directions right now. Verify those later. We have sigma x, right? Sigma y, tau xy, and tau yx. So to figure out where those are, right, we've got to figure out these points on our Moore circle that are oriented at 114 degrees from our known stress state, okay? Our known stress state being these 2 points on our Moore circle. So if we look at sigma x, right, our sigma x is going to equal the center plus the radius times the cosine of alpha. Other way around. Subtract it. Right? So if we visualize this power of Moore's circles, you're visualizing the stress state. If we drew a line at 114 degrees, like it kind of did, okay, we know that we're going to be back behind the center, right? So we're really looking for what is this point? Well, it's going to be the center minus the component of the stress acted over that theta, right? Which is going to be the cosine of alpha. So we've got 75 minus 75 cosine of 114, and we get 44.5 megapascals. Sigma y, well, that's C plus R cosine alpha, right? Now we're past the center, so we're going to take the center plus we're going to add in this horizontal component. So we get 75 plus 75 cosine of 114. We get 105.5 megapascals. And tau xy. Well, tau xy is essentially just the vertical component of this radius, right? It's going to be equal above and below. So we can say that tau xy is r sine of alpha, right? So we've got 75 times the sine of 114. 68.5 megapascals. So now that we have these magnitudes, right, we've got 44.5, 105.5, and 68.5. Well, if we're looking at the x face now, well, the x face we know is positive, so it's in tension, so the direction of my arrow, I guess, was right. Then we also know that we're above the x-axis, right? This is clockwise rotation, so the direction of this shear stress on the x faces should try and spin this stress block clockwise, which I did, guess that right. And then the other side, right, in the y direction, Okay, we're gonna be past the center, we're at 105.5 megapascals. It's on the tension side is positive, so it's acting outward from the face. And then if we look at our shear stress, right, we're on the counterclockwise rotation. So it's going to be trying to twist our element counterclockwise, so that'll give you the sign of what the shear stress direction is. So we essentially get 105.5 megapascals in the y direction, and we get, what is this, 44.5 megapascals on the x direction, and our tau xy and tau yx are equal, and they're 68.5 megapascals, right? And if we look back at our derivation before, where we cut all these lines and then figured out the geometry and figured out the components, and luckily we had derived this equation already, right? And this is just for axial load, okay? We established these same magnitudes, right? Sigma x was 44.5, sigma y was 105.5, and tau xy and tau yx were 68.5. And they could ask us, what is it at 75 degrees? What is it at 100 degrees? And we can figure out exactly what the stress state is. Right? The other benefit here is if our material that we were using had a maximum shear stress, like maximum allowable shear stress, right? We can figure out the maximum shear stress, which is essentially the radius. We could compare that back to what our allowable shear stress was and see if our material was overstressed. Also, we have our principal stresses, which in this case are principal stresses, right, which is our normal stresses where we do not have any shear stress. In this case, it was our initial stress state because we have axial load only, okay? But if we have torsion and other things adding to it, those principal stresses might be different. And so we can figure out what the maximum normal stress in the material was, and we can relate that back to what is allowable in the material. Okay? All right, let's do another example. So I feel like I got through to you a little bit, but got a little more work to do. All right. Kind of going back to that initial stress state problem we did, right, where we had two torques acting on a pipe, and then it had an axial load. In this case, we have a solid shaft that undergoes a point load, right, a tensile load of 30 kilonewtons and a torque of 100 newton meters. They're acting as shown, and we want to know what is the stress element, illustrate Moore's circle, and determine what are the principal stresses and the max shear of this shaft, right? Because ultimately we would relate that back to the allowable stresses of that material and make sure that it was adequate. Okay. Well, let's do the solution. Well, if we go back to our definition, buttons. We go back to our definition of stress. Force over an area. So we're going to populate this stress element H. Okay? We're going to orient H along the axis of the member, right? So the angle of rotation it's running along the axis of the material. So we've got H. So we're going to try and populate this stress element. Okay, so we know there's going to be a normal stress in this shaft, right? That's going to be acting on the sides of the stress element H. That stress is going to be P over A. We know P is 30 kilonewtons, right? An area, well, that's pi over 4 times the diameter squared. Well, that's 20 millimeters. Or 314.6 or 0.16 millimeters squared. Okay. So that results in a normal stress of 30,000 newtons over 314.16 millimeters squared. We get 95.5 megapascals. We can all agree that that's going to be the normal stress throughout this whole shaft, right? You cut this shaft and looked at a free body diagram along its entire length. So we got to the support where we have a resisting force. That normal tensile stress is going to be acting along the entire length. Also, we're going to have shear stress because we have torque, right? We know by now torque applied to a shaft, right? Whether it's a pipe or a solid shaft induces shear stresses in that shaft. Those shear stresses are relative to the distance from the center, right? We have zero shear stress at the center. We work our way out to the outside. So if we look at a torque like we have here, draw a little circle. Right, we have this sort of behavior going on. We went through that derivation in the notes. So our maximum shear stress is the torque times our max radius divided by the polar moment of inertia for the shaft, right? So if we were looking for the max shear, we'd use this TC over J equation. We know T equals 100 Newton meters. Our max radius, well, that's the diameter over 2. Get 10 millimeters. And we know for a solid shaft, pi over 32 times the diameter to the 4th. So that's 15,708 millimeters to the 4th. So now knowing all of our parameters, we can plug in and figure out our maximum shear stress. 100 Newton meters. I'm going to move this to millimeters times our max radius divided by 15,708 millimeters to the 4th. And we get a shear stress of 63.7 megapascals. So now that we know the shear stress and the normal stress acting within this shaft, we can populate a stress element. Right? We know what stresses are acting along this shaft, so we can populate a stress element. So if we look at our stress element at, say, H, right, that's our point H, that little dot there. We've got sigma x equal to 95.5 megapascals, right? Shear stress, looking at this element, right? Because of the torque direction, it's going to be acting downward in the right-hand face of this element. If it's acting downward on the right-hand face, it's going to have to act upward. And we know from equilibrium, we're going to need these other two shear stresses, right? We're going to have shear stress on all four sides. We have it on one side, we have it on all four sides. We're going to say tau xy, tau yx are equal, and it's 63.7 megapascals, right? We could potentially, this was a pipe, maybe it had fluid in it, it was running under pressure, okay? We might have what we call hoop stresses, we'll talk about in class later. And then we might have a normal stress in the y direction, right? But because we don't have this, there's no normal stress in the y direction. This is our stress state, right? This is a stress state of an element oriented as shown. Well, now they ask us to illustrate Moore's circle based on this stress state. and we want to determine what are the principal stresses in the max shear. Okay? So we are going to go for old Moore's circle. I'm going to draw it really well. Got our two axes. My initial stress state has a lot of normal stress in one direction and not a lot in the other, right? You can really be assured that we're going to be on the right-hand side, or really close to the right-hand side of our Moore's circle, right? To the right side of the y-axis. Remembering that our y-axis is our shear stress, counterclockwise on the bottom, clockwise on the top. Our normal stress is on the x-axis, positive to the right. So now we need to plot our two coordinates, right? We've got these coordinates from this initial stress state that we developed. We've got our coordinates on the x base. Well, in this case, we've got a normal stress of 95.5 and a shear stress of 63.7. So we essentially need to figure out where the hell we're going to say that is. So I'm going to say it's like right here. This is going to be sigma x comma tau xy, right? Which is 95.5 comma 63.7. Right? That's the coordinate of the x phase stress. Because it's also going clockwise, right? So it's above the x-axis. Because our shear stress is rotating this clockwise, we're above the x-axis. We have 63.7 y-axis value, x-axis 95.5. That's our normal stress. It's tension, so it's positive. It's on the right-hand side. Then we're going to go and we're going to do our. Wow, this is going to screw me up. That's all right. We're going to do sigma y comma tau y x, right? Which in this case, our coordinates are 0, 63.7. Our shear stress on the y face makes this rotate counterclockwise. So now we can draw a circle, which this is really going to test my abilities here. It's scaring me. Oh, shit. That ain't bad. Right? So we can now draw a circle based on those 2 points. It might be easier to establish the center first, and then you could run a radius, and then you know what the radius is. But we will finish this problem on Friday. There is a quiz this week, okay? It'll be available tomorrow as normal, available through Sunday. Remember to take your time, use the text, right? That's free to use. Yes.
So what did I do at midnight or 5?